Okay, from here we reach the end of lecture 7 and we are moving to lecture 8. In the lecture 8 we will discuss about some applications of recursive definition. And before we go for this, let's just remind ourselves what do we mean by a recursion or recursive or recurrence. Recursion is the general term for the practice of defining an object in terms of itself or of part of itself. So previously, we saw that we can find the term of the sequence based on the term before that comes before. Or we can have the value of the term based on the position itself. So here we can see that the recurrence or recursive is a continuous process of repeating itself or part of itself. Now, finding the GCD of two integers is one of the famous applications of recursive definition. And here, when we speak about two integers, we speak about a large number, right? So in order to find the GCD of any two numbers, all what we do is find the factor of the first number, the factor of the second number, and then we are trying to find the greatest common divisor between those two. However, if I got a large number, then there will be a lot of factors and it will be quite harder for us to find the GCD. Now, recursive definition make it easy. Says that GCD of x and y is equal to x if y is 0. Otherwise, what we do is we find GCD of y x mod y, and I know that you know what do we mean by mod, where we can substitute it with the remainder here. Okay, let's see this example and I'm sure you will get it. We need to find the GCD between 270 and we put in our mind, if we reach the GCD x and y, where y equal to 0, then GCD is x. Otherwise, all what we need is take y, put it in the front, and then find the value of x mod y. And we'll keep doing this until we reach here y is equal to 0. Okay? Now, from here, we'll have the question as GCD 270. We can see here this is x and this is y. Y is not equal to 0. Then we can have it as GCD 70 200 mod 70. So we put y in the front and then we try to find the remainder if I divided 200 by 70. All right, this is equal to GCD 70. If I divided 200 by 70, then I'm getting 60 as the remainder. Again, we ask, is y here equal to 0? No, then I need to repeat the mod process here. So here we got that this is equal to GCD 60, then 70 mod 60. Okay, and here we got that GCD here is equal to 60. If I divided 70 by 60, then I'm getting the remainder as 10. Did I reach y equal to 0? No, then until now I didn't find the GCD. Okay, so we'll keep doing this again, finding the remainder. So here we got that GCD 10 and 60 mod 10. All right, and this is equal to GCD 10. If I divide 60 by 10, then I'm getting the remainder as 0 because 10 is one of the 60 divisors. Now you can see here that I reach y is equal to 0. So from here we can find that GCD 270 is equal to 10, which is the value of x here. And by the way, this example is not in your material, therefore you can use the concept here to solve the material and then check your answers in the examples itself. Let's see another application here. Here it asks to give a recursive definition of the subset of non-negative integers, which is z plus, consisting of all powers of 5. Here we can see this is my relation. I need to find the recursive definition. Now, in order to find the recursive definition, if you remember, we say that it is a combination of recurrence relation and initial condition. Now, in here, the recursive definition consists of two main things, the same as what we said earlier, which is, first of all, base step, where we define the relation, and then we have the recursive step. Now, what is in the base step is where we specify the values of the function for the first terms. Specify the values of the functions for the first terms. So from here, we can see that in the question, it asks that the non-negative integers is there. All right. So here in base step, we know that all z plus is included in this definition, and z plus is equal to 0, 1, 2, and so on. Okay, this is the base step where it is in the previous definition as the initial condition. Okay, now in recursive step, we can see that, let's say C is a subset of Z star, where C is equal to powers of 5. And powers of 5 is 5 to power 0, 5 to power 1, 5 to power 2, and so on. Okay? Now, if we say that 5 is an element of C, okay, and fx is an element of of C again, then five times x is also will be an element of C. And here we find the recursive definition of a subset of non-negative integer consisting all powers of 5. Again, in order to find the recursive definition, we need to find the base step, where we specify the values of the function for the first terms, and recursive step, where we give the rule for finding a subsequent values using the previous values beginning at these defined in the base step. Okay? Alright, one more example here where we need to find the recursive definition for the set of palindromes over the set A. Now we got here in set A as A and B, okay? And we need to find the palindromes, okay? Again, base step and recursive step. Okay, now in base step we say that A have got A and B as the value of A. Okay, now the set of palindromes over A palindromes is, and let's say we give it the value as L. First thing is we got lambda, which is nothing in there, or it can't be A, B, or A, B, B, or A, B, A, B, A, and so on. Okay, and lambda is like the empty set. Okay, now in recursive step, if we say that X is an element of L, where we defined it here, then for sure A is an element of L and B is an element of L, because L is a subset of A, right? Okay, then if I have a combination as AXA, it should be an element of L, and BXB, a combination of the second letter, is also an element of L. All right? Okay. Now the last example in this session is asking us to find the n-bit binary string over the set A, 0 and 1, where they do not contain 0 and 0. Now, in order to solve this example, we need to do it step by step, okay? Let's say, again, we got that base step. Okay, and base step, it depends on the how many bit in the binary string, okay? If we say it's like n is equal to 1, which means 1 bit string, then my set will contain only either 1 or 0. And if you notice here, the number of the values in my set 1 is equal to 2. If we say that n is 2, which means 2-bit string, then the values in my set, it might be either 0 or 1, 0, 1, 1, 0, 1, 1. And if you notice here, we eliminate the 0, 0 because it should not contain 0, 0. And from here we can see that the values of the set is equal to 3. All right, now let's suppose I got n as 3, which means they are 3-bit string. Okay, now B3 is equal to, where I have 3-bit strings, then it might be 0, 1, 0, 0, 1, 1, 1, 0, 1. So here I'm speaking about the possibilities, all right? Then we got 1, 1, 0, 1, 1, 1. And again, I'm eliminating all the bit string that contains 0 and 0. And from here, we can see that the number of elements in this set is equal to 5. Now, if we says that n bit string, I don't know how many bits in the binary string. Okay, then we can see that we have two cases. Okay, case 1 and case 2. Case 1, if my bit string starts with 1. Okay, so it will look like something like this. So my Bn is equal to 1, A2, A3 until An. I will have a specific recurrence relation. Case 2, it starts with 0, then my bit string will be something like 0. Then for sure it should contain 1, and then we can have any of the bit string, either 0 or 1. So we'll see each case the recurrence relation. So for case 1, where the bit string starts with 1, okay, A2 can be either 0 or 1, which is fine. I can use either 0 or 1. So from here we can see that B, the value of depend on the value of the first one. Okay, if we go here, we can see that if it starts with the 0, then here I don't have an option. It should be 1 because it does not contain the bit string with 0 and 0. Okay, therefore we can see here that the term depends on the previous one. So A3 depends on here, okay, which is Vn minus 2. So from here we can see that the recurrence relation okay is Bn is equal to Bn minus 1 plus Bn minus 2 for all n is greater than or equal to 3, where the initial condition, which is B1, two, and B2 is equal to 3. And here we reach the end of this session where we discussed about the recursive definition and simple problems, where we find the recurrence relation of a sequence, or we can find the sequence for the recurrence relation. And then we discussed about the recursive application, where we use the recursive definition for GCD and for the other applications. Thank you for the good listening, and we'll see you inshallah in the next session.